Hello Chemist Corner. Welcome to Electrochemistry. Today we will be balancing redox reactions, and we'll start using the half-cell method. Consider the reaction you saw in the first video, the reaction between copper 2+ ions and aluminum metal. It actually happened. Therefore, the delta G for this reaction must be a negative, and the E0 cell must have a positive voltage. That is, the E0 reduction for the copper plus the E0 oxidation for the aluminum must add up to be a positive value. Sure enough, the copper has a 0.34 voltage, the aluminum a 1.66 voltage, for an overall positive voltage for the E0 cell of 2.0 volts. However, copper gained 2 electrons and aluminum lost 3. The electrons gained by copper must be the same electrons lost by aluminum, therefore they must be equal. Some balancing is now required. Because the lowest common multiple between 2 and 3 is 6, 6 electrons are lost and 6 electrons are gained in this process. In the demonstration done for the first video, you can see the aluminum foil reacting vigorously with the copper 2+ ions in solution. What you can't see is the temperature has increased dramatically during this process. However, what you can see is the loss of copper 2+ ion color from solution. The blue color has gone away, forming a clear colorless solution. What else you can see? The formation of the brownish red precipitate, which is 0 copper, that is neutral copper metal, which quickly settles to the bottom of the beaker. When the half cells in a redox reaction are more complicated than simple metals and simple metallic ions, this is the process we should follow. The first step, balance any element other than hydrogen and oxygen. Second step, balance the oxygens with water molecules. This, of course, will introduce some hydrogen ions, so our third step, balance the hydrogens with hydrogen ions. Next, the fourth step, balance the charges with electrons. For our first example, consider the reaction of nitrate to nitrite. This is the reduction. The nitrogens are already balanced, but the oxygens, of course, are not. So add 1 water to the product side. My oxygens are now balanced. Next, add 2 hydrogens to the reactant side to balance out the hydrogens from the water. Finally, step 4, add 2 electrons to the reactant side, so both sides of the equation now have a net -1 charge. This reduction reaction is now both matter and charge balanced, but it's only half. Now consider the oxidation of chromium to chromate. The chromium atoms are already balanced 1:1, but the oxygens, of course, are not. So introduce 4 waters to the reactant side to balance the oxygens. Now, add 8 hydrogens to the product side to balance out the hydrogens you introduced with the water. Finally, add electrons, 3 of them, to the product side to balance out the charges. This oxidation half cell is now, again, both matter and charge balanced. The next step is to equate the number of electrons gained by the reduction to the number of electrons lost by the oxidation. Of course, the nitrate gained 2 electrons, it got reduced, and the chromium lost 3 electrons to become chromate. That 2 and 3 need to become a 6. So we multiply the 2 electrons gained by the nitrate by 3, and we multiply the 3 electrons lost by the chromate by 2, so we have 6 electrons gained and 6 electrons lost. Next, we combine the 2 half cells and simplify by canceling out the electrons. After the electrons have been canceled, we can further simplify by canceling out 3 waters from both sides and canceling out 6 hydrogen ions from both sides. That leaves us with 5 waters on the reactant side and 10 hydrogen ions on the product side. My overall balanced equation then, 5 waters, 2 chromium 3+ and 3 nitrates, produce 3 nitrites, 2 chromates, and 10 hydrogen ions. This is now the complete cell, and it is both matter and charge balanced. The second method to balance redox reactions is called the oxidation number method. But before explaining how to balance an equation using the oxidation number method, first we must establish what is an oxidation number. An oxidation number, then, is the real or apparent charge on a single atom when all bonds in a structure are assumed to be ionic, based on the relative electronegativities of the atoms involved in that bond. Any atom in its pure elemental form will be assigned an oxidation number of 0. For instance, neutral copper, 0. Chlorine gas, 0. Sulfur, yellow sulfur in the form of S8, 0. And of course, aluminum metal also an oxidation number of 0. For any simple ion, the charge on that ion is its oxidation number. A lithium 1 plus, oxidation number plus 1. Zinc 2 plus, oxidation number plus 2. A nitride, oxidation number of minus 3, and an iodide, oxidation number of minus 1. Our third rule for oxidation numbers: the oxidation number on oxygen is always assigned to be a minus 2 unless it's in its elemental form. Rule number 1, its oxidation number would be 0. Or if it's a peroxide, that is a polyatomic ion of 2 oxygens bonded together with a net negative 2 charge, in that case, its oxidation number will be minus 1. Our fourth rule involves hydrogen. The oxidation number on hydrogen is always assigned to be plus 1 unless it's in its elemental form, again, according to rule 1, or if it's a hydride, which is a simple ion of minus 1, in which case its oxidation number would also be minus 1. The fifth rule: for any molecule or polyatomic ion, the simple sum of the oxidation numbers of all the atoms in the structure will equal the net charge on the overall particle. In the example of methane, CH4, if we use the previous rule, hydrogen has an oxidation number of plus 1. 4 hydrogens contributes plus 4 to the overall structure. Since the overall structure has a neutral charge, carbon, therefore, must have an oxidation number equal to minus 4. In our next example, the sulfate ion, we apply the third rule: oxygen always has an oxidation number of minus 2. There are 4 oxygens. That contributes negative 8 to the overall structure. The overall structure, sulfate, has a net charge of negative 2. Since the oxygens contribute negative 8, the sulfur therefore must have an oxidation number of positive 6. The sum of the oxidation numbers equals the net charge of the overall particle. To summarize our oxidation number rules, rule number 1, any element in its elemental form has an oxidation number equal to 0. For any simple ion, the charge on that ion is its oxidation number. The oxidation number of oxygen is assigned to be a negative 2 unless it's in its elemental form or it's a peroxide, in which case it's a minus 1. The oxidation number for hydrogen is always a plus 1 unless it's in its elemental form, 0, or is a hydride, negative 1. For any molecule or polyatomic ion, the sum of the oxidation numbers for all the atoms in that species equals the net charge on the overall particle. Here are a couple more examples for rule number 5. For any molecule or polyatomic ion, the sum of the oxidation numbers equals the net charge on the overall particle. Here we have permanganate, MnO4 minus 1. 4 oxygens, each a minus 2, adds up to minus 8. Net charge is negative 1, therefore the manganese in permanganate must be a plus 7. For phosphate, 4 oxygens times minus 2 equals minus 8. The overall charge on phosphate, of course, is minus 3. Therefore, the phosphorus in this state must be a plus 5. In the dichromate polyatomic 7 oxygens, minus 2. 7 times minus 2 gets minus 14. The net charge is negative 2, so the 2 chromium atoms contribute plus 12. Each chromium atom, therefore, must contribute a plus 6. 12 divided by 2 is plus 6. In the case of the inner transition metal uranium, we get a different situation. 3 uraniums and 8 oxygens make a neutral compound. 8 oxygens, minus 2 each, contribute negative 16. The net charge is 0, so therefore my 3 uraniums must contribute a positive 16. 3 uraniums, positive 16, therefore each uranium will be assigned an oxidation number of 16 divided by 3, or 5 1/3. It is possible to get a fractional oxidation number for some transition metals. For our last example, we look at sodium phosphate. We know it has 4 oxygens, minus 2 each, that contributes negative 8. Sodium, being an alkali metal, can only have an oxidation state of 0 or 1. In this case, it's an ion, so it's plus 1, so it's contributing plus 3. The oxygen's minus 8, the sodium's plus 3. The charge on the overall structure is 0, so therefore phosphorus must have an oxidation number of plus 5. Now that we have a reasonable grasp of oxidation numbers, we can attempt to balance using the oxidation number method. To balance by the oxidation number method, the first step is to determine the oxidation numbers of any species whose oxidation number changed during the reaction, and then determine the amount of change according to their oxidation numbers. For the example of aluminum metal reacting with a sulfate ion, first find the oxidation numbers of aluminum sulfur on both sides of the equation. Aluminum metal has an oxidation number of 0, aluminum ions plus 3. The change? It went up by 3. The sulfate ion has an oxidation number on sulfur of plus 6. The sulfite ion, an oxidation number of plus 4. The change is 2. The change in the oxidation state is the number of electrons transferred. Therefore, we multiply each pair to equate the number of electrons. I need 2 aluminums to give 6 electrons transferred, and 3 sulfates to get 6 electrons transferred. Now that we have the right number of electrons transferred, we can balance the number of oxygens by adding water molecules. In this case, we need to add 3 water molecules to the product side. Fifth step, balance the hydrogen atoms by adding hydrogen ions to the other side of the equation. Since we added 3 waters, we added 6 hydrogens, so we need 6 hydrogen ions to the reactant side. Finally, we can check our balancing by comparing the net charges on both sides of the equation. And in this case, our net charge is 0. In our next example, we will balance by the oxidation number method again, but this time under basic conditions. In the reaction between magnesium metal and chromate ions, first, find the oxidation numbers of magnesium and chromium on both sides of the equation. Magnesium metal 0, magnesium ions 2+. The oxidation number of chromate, chromium in chromate, is 6+. The oxidation number of chromium 3+ ions is, of course, plus 3. Next, determine the changes in the oxidation states for each atom. For magnesium, it's a plus 2. For chromium, we went down by 3. The third step, the change in the oxidation state is the number of electrons transferred, and those electron transfers must be equal. So I multiply my magnesium half by plus 3, and I multiply my chromate half by 2. Again, 6 electrons got transferred, 6 electrons lost by the magnesium, 6 electrons gained by the chromate. This time in our fourth step, instead of adding water, I'm going to balance the charges by adding hydroxide ions. In this particular example, I need 16 hydroxides to balance all those negative charges. Next step, fifth step, is to balance the hydrogen atoms by adding water molecules. In this case, I need 8 water molecules on the reactant side. And finally, we check our balancing by comparing the number of oxygen atoms on both sides of our equation.